Hello everyone, I'm Sonja Englert and I want to welcome you to my airplane design tutorial number 4. I hope you have watched the previous ones because I have arranged them in sequence to provide step-by-step instructions on how to go about designing an airplane or simply to learn more about how this is done. In the last one, I talked about how to get started designing the fuselage by drawing its shape, determining the position of the landing gear, and placing the coordinate system. In this video, I will continue with the fuselage design and focus on the center of gravity and how to calculate it, the mass distribution, and how to mate the wings with the fuselage. So let's get back to the fuselage. In this view, I have drawn in a few more details of the fuselage. It has a preliminary tail and gear positions. Where the wing can be positioned is influenced by several factors. First of all, there has to be room to route the spars or the spar through the fuselage without interfering with other components. The aerodynamic center of the airplane, which is largely determined by the wing, and the center of gravity of the airplane, which is determined by the mass distribution, have to be at a certain distance from each other. The CG must be in front of the aerodynamic center, otherwise the airplane will not fly stable. But at this point, we do not know where the CG or the aerodynamic center is. It is like the problem with the chicken and the egg. So to start with, we just draw up something that looks nice and iterate by moving things around until we know more about both missing numbers. We need to talk about the center of gravity for a while. First of all, we will rehearse how to determine it on an existing airplane with the whole airplane set up on scales. Set the scales to 0, then roll the airplane up. It needs to be leveled, that means the waterline or x-axis is horizontal. For this example, I use a nose gear airplane and the reference plane is at the wing leading edge at the root, so anything forward of the wing leading edge has a negative fuselage station. In this table, enter the weight readings W1, 2 and 3 in the center column, which is shaded yellow for input data. The airplane can then be removed from the scales. Use a plumb line to mark the spots directly under the wheel axis centers on the floor for all 3 wheels and the wing leading edge, which is our reference in this example. Measure the distance from each main wheel center to the wing leading edge line. This is a positive number because it is aft of the reference line. Measure the distance from the nose wheel to the reference line, which is a negative number, and enter the number in the table as the fuselage station. Multiply the arm and the weight to obtain the moment. Add all weights, this is the empty weight. Add all moments and divide the total moment by the total weight. This is the empty weight CG, or rather its distance from the reference line. It does not matter where the reference line is. Just remember that the result is always a distance from the reference line. Calculating the CG of an airplane when a change has been made, for example when a battery is moved from the front to the back, or when another item was added to the empty weight, is very similar. I'm using the second table to show an example. This time, enter the old empty weight and CG at the top. Underneath, list the old, new and new location of the battery. The removed battery weight needs to be entered with a minus sign and with a plus sign where it is reinstalled. The new instrument is simply added. Calculate the moments and add them for the total moment. For the total weight, add all the item weights. The moved battery has no effect on total weight, just on the CG. To get the new CG, again divide the total moment by the total weight. So you can see that this is a very simple calculation. Now we are ready to get back to the fuselage design problem. To calculate the CG of the new fuselage, we need to have a pretty good idea of the weight of all components that will go into the fuselage and also the structure itself. So far, we have only used the x-coordinates or fuselage stations of the items we calculated. We will need to have x, y, z coordinates for all discrete weights and to eventually calculate the fuselage load. Typically, for small airplanes, the only parts with y coordinates other than 0 are the wings, horizontal tail, and main gear. The sketch shows how all items are turned into numbers of mass and coordinates. Obviously, this involves a lot of estimates, which is okay. The fuselage structure, which is still unknown, will be divided up into segments. This information is entered into a table. A simple example is shown here. The items should be listed in the proper sequence, front to back. The weight of the wings is divided up on the front and the rear wing attach fittings. Once all the weights are added up, the result must be equal to the projected empty weight. Then you can proceed with calculating the CGs in X, Y, and Z direction. Now it becomes a little tricky, because the CGs need to end up in the right place, for example at the forward limit or aft limit, as required by the loads analysis. As shown in this sketch, if there is a heavy engine up front and a light tail in the back, it may be necessary to shift some of the weight aft to level the balance. This is obviously much easier to do at this stage of the design than after the airplane has been built, so it is worth paying attention to it. When the CG is right where the support is, the balance is level. The weight and CG envelope limits may look like something shown here. The units of the arm are not inches or meter, but percent mean aerodynamic chord, which is a percentage of the MAC chord of the wing. I will explain what and where MAC is in another tutorial. For now, let's just say that it is a convenient way to give the CG position in a way that can be compared directly from one airplane to the next. The range shown here from 19% to 24% is a good range for any conventional small airplane, although there are cases when the CG can be safely moved further forward or back. You can use this range or something a bit wider to start with. The final CG limits will be determined during flight test. In order to calculate the CG from the fuselage mass table, use the same procedure as explained before by calculating the moments. Of course, the CG never comes out right to start with, so you will have to shift some weights around to make that happen. It will also show clearly if at this stage the mass distribution is so impractical that the airplane has to be redesigned. Getting the weight and balance right is one reason why we're doing this. The other reason is that this table is needed for the loads analysis. The loads in turn are needed to design the structure so that it is strong enough. You will realize that this is another chicken and egg problem. Without the mass distribution, we cannot calculate the loads, and without the loads we cannot come up with a structure that is part of the mass distribution. So how is this solved? You have to start out by gathering as much information on the weight of the items that will be installed in the airplane, including engine, occupants, baggage, and fuel. Add it up and see what is missing to make up the difference to the projected empty weight. This difference is the structure, which is divided up into separate masses according to the dimensions of the fuselage. This will get you pretty close, and this will be suitable for the loads analysis. Of course, once loads and structure were calculated, you can go back and refine the initial assumptions. Again, use as much information as you can find from existing similar airplanes to help with this. So far we talked about the wing and fuselage separately, but of course they will need to be joined together. The positioning of the wing on the fuselage relative to other parts of the airplane is obviously very important. As I have already hinted at, the position of the aerodynamic center of the airplane is mainly determined by the wing. The aerodynamic center of the whole airplane is that one point where we imagine all the aerodynamic forces created by the airflow are combined into one vector. The procedure is to design the wing and fuselage separately, determine the wing aerodynamic center, and attach the wing to the fuselage so that the center of gravity of the whole assembly is slightly ahead of the wing aerodynamic center. Obviously, the shape of the fuselage has to fit the wing. You have seen the results of this in the fuselage mass table, where the wing shows up in the form of its front and aft attach points. I assumed here that the wing CG is at 50% of the root chord and have distributed its weight evenly between front and aft attach points. I want to conclude the video here and continue next time with the discussions on the tail design.